Lab 4, Rope Physics and Spring Mass System. The objective of our lab, we will predict the motion of a spring mass system using Newton's second law. The mass swings in an arc while oscillating on a spring. Then we will use our prediction to analyze the energy principle. Here we have our spring. The initial length at static equilibrium is 0.7 meters. The positive x direction goes to the right. The negative y direction goes down. First, we track the motion. We edited our Python starter code by inputting our initial characteristics, the spring force, the gravitational force, Newton's second law, and the energy principle, along with its components. Finally, we analyzed our predicted motion and the energy graphs. Our model was accurate, but there were some incongruities which we will discuss. Our initial characteristics, the initial time is 0, which we put here into our code. The mass was 0.402 kilograms. The initial x position was negative 0.109. The y position was negative 0.637, and that position is put in here. The initial velocity was 0. We assume that it is 0 because the mass was held and then let go. We put in the gravitational constant for the Earth. We put in the spring constant here, which is derived from what we know of our period. Our period equals 2 pi times the square root of the mass over the spring constant, and we arrange that equation so that k equals 4 pi times the mass over the period squared. We find our static equilibrium of the spring without a mass attached here, and we find that by setting the mass times the gravitational constant of the Earth equal to the spring constant times the length of the spring at static equilibrium with the mass minus the length of the spring at static equilibrium without the mass. The fundamental principles we used Newton's second law, which is put into the code here. The F net force is equal to the gravitational force plus the spring force. Then we enter our energy principle here. We enter the kinetic energy, the potential gravitational energy, and the potential spring energy. And we also enter the change in the kinetic energy, the change in gravitational potential energy, and the change in spring potential energy here. When we run our code, we see that the blue ball is our predicted position and the red ball is our observed position. The red ball is a little bit jumpy because we predict our position way more often than we track the position. And we can see here that the red ball is deviating from the blue ball, and this is because of drag and also because the numbers we used for the gravitational constant as well as the stretch are estimations. When we look at our graph, we can see that the kinetic energy is going up and down, and so are the spring potential energies and the gravitational potential energy. As the gravitational potential energy increases, the spring potential energy decreases, and as the spring potential energy increases, the gravitational potential energy decreases. When we look at our what does it mean question, at first look it appears as if the total change in energy is 0. The yellow line here looks like it is 0 the whole time, but when we look really close it is revealed that the change in total energy is not 0. This is the total change in energy when we look at it up close and just at the change in total energy. This is because the gravitational constant we used as well as the spring constant and the stretch are estimations. This change in energy is so small that it is negligible, so we can say that no energy was added or taken out of a system including the Earth and the spring mass system. So energy is conserved. Our what if question. So we take 3 periods from our tracker, and to get a good estimation of the real period we divide that by 3, and our estimated period for the y component is 1.517 seconds, and our estimated period for the x component is 1.646 seconds. The periods are different because In the x direction, the gravitational force is constant, and the spring force is the same at each extreme. In the y direction, however, the gravitational force is constant, but the force of the spring is different at the extremes. In conclusion, we analyzed the motion of a mass swinging in an arc while oscillating on a spring. Then we modeled the motion with a Python program and graphed the changes in different energies. Finally, we analyzed the accuracy of our model as well as the periods of the x and y components of the motion and discussed the application of energy principle to this situation. Thank you for watching my Lab 4.